So, welcome back to the lecture series of communication system. In this lecture series, I am going to discuss about the probability density function. So, probability density function basically it is a statistical expression and it defines the probability distribution for a discrete random variable. I'm already discussed about the discrete random variable. So here this probability density function is actually define probability distribution for a discrete random variable. So then we discuss a example of the probability density function. So when the PDF is graphically portrayed, the area under the curve will indicate the interval in which the variable will fall. The total area is this interval of the graph equals the probability of a discrete random variable occurrence. More precisely, since the absolute likelihood of a continuous random variable taking on any specific value is zero due to infinite set of possible values available, the value of PDF can be used to determine the likelihood of random variable falling within a specific range of value. So basically, probability density function is a statistical measure and it is used to measure the likely outcome of a discrete value. For example, a price of the stock market. So the probability density function that is also called the PDF is basically plotted graphically and it's just like a bell curve when the probability of outcome lying below the curve. So that if you see the graphical representation of a PDF, so it is just like a bell curve and all the values are coming inside the particular curve. So a discrete variable can be measured exactly while a continuous variable can have infinite value. So PDF can be used to measure political risk slash reward of including a particular security or fund in portfolio. These are the basically area where we use the probability density functions. Then this see particular example. So if your x is a continuous variable, then the probability distribution or probability density function of x. So it is the probability density function of x is a function fx in a such a that for any two numbers a and b which with two number a and b which a is less than we have represented like this, it means it is represented as integration of a to b fx into ds. So the probability that x is in the interval a and b can be calculated by integrating the pdf of a random variable. So the pdf of a random variable is called fx. Similarly, the derivative of the cdf of a continuous random variable is called pdf. It means a continuous random variable that is a CDF of a cumulative distribution function of a continuous random variable. If you derive this particular variable, then the outcome is called a probability density function. So fx x is equal to dfxx upon dx. Similarly, what are the properties of the probability density function or PDF is first a PDF fx having value x is always greater than 0 for all value of x. Similarly, if we integrate this function fx from minus infinity to infinity, its value is it become 1 and then fx equal to minus infinity to x where fxy into dy. It means fx is a function of the y. Similarly, probability of x that lies between a and b is equal to integration of PDF fx into x from a to b and with respect to the x. So these are the basically property. Then we move to the joint probability function. So any random variable CDF is defined as fx into x where that is equal to probability of x less than equal to x. So now if the two random variables are f random variable x and y, then we have defined a joint cumulative function. So it is represented as fxy into fxy, that is the function of x and y that depends on probability of x less than equal to x and y less than equal to y. That is equal to the probability of x less than x and y is probability of x less than, that is the intersection of x and y. So these are the basically joint cumulative function. Similarly, cumulative joint PDF often encountered when dealing with combined experiment or repeated trial of single experiment. Multiple random variables are basically multi-dimensional function defined on a sample space of combined experiment. For example, experiment 1, x1, that is equal to outcome is x1, x2 and so on. And similarly, experiment 2, outcome is y1, y2 and so on, yn. If you take any one element from x1 and x2, then its value is like pxi yi, and it varies from 0 to 1. That is called the joint probability of two or more outcomes. Then there are marginally probability distribution that is represented as sum of the j or sum of the I and j are just a variable that is the function of xi into yi, and that is a function of either xi or yi. Then, what are the expectation of a random variable, that is also called statistical average? So, statistical average are moments play an important role in characterization of the random variable. So, first moment of probability distribution of a random variable x is called the mean value. So, mean is represented this particular formula represent the mean of this particular random variable. Then there are the mean square is represented by here. See this both the expression here we write x and then it is mean square, so it is x square. Similarly, central moment are moment of the different function x and mx, and second central moment is variance of x. So the variance is defined as ex minus xn square. See this particular formula. That formula is, these are formula that will be directly written here. Similarly, this particular variance is equal to the difference between mean square value and square of the mean. So it is represented by using this formula. So it is equal to the mean square value and square of the mean. So in this way we are able to calculate the first, it is first we are able to calculate the mean value, then we are able to calculate mean square and then variance of a random variable. Then the variance provides a measure of variable, it means randomness, and mean and variance of the random variable give partial description of its probability density function. Then the next topic is time averaging and ergodicity. So a process where any member of ensemble exhibit the same statistical behavior as that of the whole ensemble. For ergodic process, to measure various statistical average, it is sufficient to look at only one realization of the process and find corresponding time average. For a process to be ergodic, it must be stationary. So that, and but the convergence is not true. So that is the basically definition of averaging and ergodicity. Similarly, in the case of the continuous random variable, its PDF is defined like this: 1 upon root this and exponential function where mu and sigma square are the parameter usually denoted as n mu square. Now, important and frequently encountered random variable is this, so it is the graphical representation of fx into fxx, and similarly its probability fxx. So see here, this particular curve, it means this particular probability density function is actually a bell curve, that we have already discussed in the previous slides. Then what is the wide sense stationary process? A process that following these two conditions is called a wide sense stationary process. So second order stationary, wide sense stationary, but its convergence is no. It means a second order stationary process is called a wide sense stationary process, but a wide sense stationary process is never called a second order stationary process. Then ergodicity, attribute of stochastic system, generally a system that tends in probability to a limiting form that is independent of initial condition. Time average of a quantity is defined like this. Here A is used to denote time average in a manner analogous to E, ergodicity for statistical average. Then the time average is taken over all time because as applied to random process, simple function of processes are presumed to exist for all the time. Let then it's just given an example. Let xt be a sample of a random process. Xt where the lowercase letter imply a sample function, but this function is not a random. So see here the sample space is represented as the x1, x2, xn, xn minus 1, n plus 1, n plus 2. Then these are the xt, that is the random process, and that is a sample of the random process. Then xt be a sample of the random process, capital Xt where the lowercase letter imply a sample function. It means a random process is represented as xt and its sample is represented as a lowercase letter small xt. So we define the mean value represented like this, and autocorrelation function is as follow. That is called basically autocorrelation function. So these are the basically averages. Then autocorrelation function for any sample function of a random process xt, the last two integral simply produce two numbers. So these two integral actually produce the two numbers. Then a number for average x, a number for a autocorrelation function for a specific value of a tau. Since the sample function xt is one out of other sample function of the random process xt, the average and autocorrelation are actually a random variable. By taking expected value of x and rxx, we obtain this, and then see here we obtain the random variable and autocorrelation functions. So these are the basically formula that is used for calculate. See here it's become a autocorrelation function that they actually try to calculate by using this these expressions. Then we move to Poisson process. So a Poisson process is modeled for a series of discrete events where the average time between the events is known but the exact timing of event is random. So a Poisson process satisfy following criteria. First, events are independent of each other, and occurrence of one event does not affect the probability another event will occur. Similarly, the average rate is constant. The event cannot occur at the same time. So if these three conditions is satisfied, this particular process is called Poisson process. Some example of the Poisson process are customer calling to the help center, the location of the users in a wireless network, the number of the car accident in a site or in an area, and movement in a stock process. These are the example of the Poisson process. Poisson process are generally associated with time, but they do not have to be. In the stock case, we might know the average movement per day, but we would also have a Poisson process for the number of tree in an acre, event per area. So if there is a lambda is greater than, we will fix the counting process is called Poisson process. Process with rate lambda if all the following conditions. First condition is n0 equal to 0, it means t equal to 0, so value is 0, and nt has an independent increment, and the number of interval in any interval of the length tau greater than 0 has Poisson distribution where lambda is arrival of event per unit time and n is the number of arrival. See this particular diagram, particular example. Number of the customer arriving in a grocery store can be modeled by a Poisson process with intensity lambda equal to 10 customer per hour. Find the probability that there are two customers between 10 to 10.2. See here lambda equal to 10, interval 10 से 10 20, the length is lambda equal to 13, that is for tau equal to 13 hour. So if x is the number of arrival in that interval, we can write x is the Poisson process, so write it is the 0.2. Similarly, we can calculate about the calculate for the second case. Then the Poisson distribution. The Poisson process is the model we use for describing randomly occurring event. We need the Poisson distribution function for finding the probability of a number of event in a time period. So Poisson distribution we write E, that is the power of event upon time into time period. This particular event upon time is represented by the lambda, so this the Poisson distribution is represented as e to the power lambda, lambda to the power k upon k, assuming that the k event in an interval, that is called the Poisson distribution. Similarly, there are binomial distribution. So a binomial distribution can be thought of as simply the probability of success or failure. Just see this example. If you toss a coin, there are only two possible outcomes, either head or tail, and taking a test could have two possible outcomes, pass or fail. So there are two examples, either we toss a coin or we take a test. So the binomial distribution is represented by this particular equation that is representing binomial distribution. Then again they are giving an example. Suppose we flip a coin, two coins, a coin two times, and count the number of the heads. So a coin is tossed two times, so the probability of is 0.25. The binomial random variable is the number of heads which can be taken on the value 0 or 1 or 2. The binomial distribution 0, 1/4 probability, 1.05, and 2 0.2 probability. So the probability distribution, I have the following. These are the basically property of the probability binomial distribution function. The mean of the distribution is equal to n cross p. P is the probability. Variance is equal to n cross p cross 1 minus p. Standard deviation is n cross p cross 1 minus p. That is called square root of this variance is called the standard deviation, where n is the number of the trials and p is the probability of success. Then the white noise. So basically white noise in a system have equal intensity at a different frequency. So it's have the equal intensity and different frequency. That's why it is called the white noise. So basically white noise is refer a statistical model for signal source rather than to any specific signal. So by the definition, a random process is called white process if xf n naught by 2 is equal to 2 for all f. So if this condition is satisfied, then it is called any random process is called a white noise. See this particular diagram. Part A show the real probability probability distribution of thermal noise. As we observed, this PSD is not constant for all frequency. However, it approximately constant. See this value, it is n naught by 2 at the center, and this value is constant from this to this. But in this interval, there are a value variation. So there are a frequency range where the probability is constant. So for the frequency range that we are interested in 2 PSD, it means this 2 PSD we have shown here. Here its value is constant, here it is not constant. So the thermal noise in electronic system usually model at white Gaussian noise process, and it is assumed that it has the zero mean and Gaussian. So these are the basically probability density of a thermal noise, and it's actually represent a white noise because in this particular frequency interval its value is constant, and the white noise have the zero mean and Gaussian distribution. So the PSD of the white noise, these are the formula that is used to calculate the PSD of the white noise, where delta t that is used at this point is called a direct delta function. Its value is defined here.
So these all about the random variable and probability density function. Thanks for your kind attention.